Okay, so when we finished off class on Thursday, we had the equation for our residual sum of squares for those three data points, and we had also computed the partial derivative of that residual of sum of squares with respect to our slope and also with respect to our intercept. So let's talk about doing gradient descent. So now what we're going to do is we are going to have two equations. We need to update the slope and we need to update the intercept. And so we have a new value for how we tweak our slope, and we have a value for how we tweak our intercept. But it's worth noting that we have a problem, which is we only did this for 3 points, and we might want to do this for 50 points or 10,000 points. So it seems like it might be a problem, but it's actually not too bad. If we just talk about the point xy, we can again figure out what's the residual, the square of the residual for that point, which means that we can take the partial with respect to the slope and the partial with respect to the bias for that individual, sorry, not for the individual, for the equation as a whole. And so we end up with these two equations. And here you go, computation of residual sum of squares and each of the partial derivatives. If you're a computer science weenie, then we're just big O of n, which is really in the number of, where n is number of samples, and that's really not bad, right? If you're looking at the textbook, which I hope you are, you should understand the notation from the textbook as well as what we've been talking about. So they use y hat of a given example to mean the predicted value, and y of e is the actual value that we had. So this is the residual, right, that we then square. And what are we adding up? Well, if we have multiple features, we need to figure out the sum of all those residuals over all those features, and also we need to go through all of the different individual points, right, data points, all the different examples. Some people like to talk about figuring out the residual and by multiplying by a half, because of course when we take the derivatives we always end up with a 2 in the front. So if we multiply by a half, that 2 cancels out. Some people like to do that, not everybody. We're not going to do that. Anyway, okay, so let's talk about, we saw that you can overshoot. We saw that if you, what have I got here? So your learning rate is too big if your magnitude of your partial derivatives are getting bigger and bigger and bigger. And so you can see that we are sort of jumping. We started with this point, and then we came to that point, and then we figured out this point, and then we ended up with this point, and then this point. So we're sort of bopping back and forth, higher and higher and higher. Bad sign, right? Bad sign. Also, if you are doing a ton of iterations and you're not moving very much at any given time, well, your learning rate is probably a little bit too small, right? And so you can, you can also, you look at what is the residual sum of squares. Is it getting bigger and bigger instead of smaller and smaller? Then your learning rate is probably too big, right? And if it's changing very, very slowly, then maybe you want to increase it a little bit. So definition, you may have heard of epochs, right? When people are talking about neural networks. An epoch is a single iteration of running your data through the network, right? So we talk about feed forward, right? If we have our layers of our network, it's pushing your input data through the network. You get your output, you compare that with the desired output, and then you use what they call backpropagation to use gradient descent to modify all the weights, right? So that's just what people mean when they talk about a backpropagation approach. We had two examples of pretty simple problems, right? Um, one or two weights, three data points, not such a big deal. When we were looking at this recognized number problem, now we've got 60,000 examples with for training and 10,000 examples as our test set. Remember when we were running this, we need to compute. We have how many weights to compute? We have all these weights, which is the 784 inputs connected to 15 of these neurons in the hidden layer. And then we have these 15 neurons here that are connecting to the what do we got here? 10 the 10 neurons on the output layer. But of course, remember that every single one of the neurons on here actually has a bias, right? And up here, we also have a bias. So we end up with 10 times 16 and 15 times 785. We add that together. We have a huge number of partial derivatives. But the good news is that we don't necessarily need to do that computation on all 60,000, weights, 60,000 trading examples simultaneously. What we can do is say, what if we split the data into what we call mini batches? And so instead of having 60,000 examples in your epoch, we say, all right, I'm going to have 6,000 data sets. Each data set has 10 examples, and then I'm going to, for every single element in my example, I'm going to say, for every batch of elements, I'm going to compute the output of the neural net for those examples and then tweak the weights. Yeah. Same number of calculations per epoch, but networks tend to train a little bit faster. Most people say it's probably because these mini batches are sort of a rough average of the bigger data set. Maybe not the 10 sample mini batches, but maybe slightly bigger ones. Useful words to use at Thanksgiving dinner when you're talking about batch size. If you say that you are doing batch gradient descent, that means you are training with the entire training set every single time. If you talk about using stochastic gradient descent, that means that you are training your batches have a size of 1, so every single element in your test set gets tested individually. And mini batch gradient descent means what you think it does. It means you make a bunch of mini batches and the size of them is somewhere between 1 and the full size of the training set. Yes, and a lot of people use these terms interchangeably, so just look out for that. Okay, so finally, a few factoids that I want you to know about, so that again you know what these terms mean. You need to be careful about not overtraining, right? How do you know? Well, you kind of know when you know, right? If your step size is close to 0, you're probably good. If you've taken way too many steps, you may want to stop. Part of the reason you need to stop before you take too many steps is the problem of overfitting. You've probably seen images like this before, but if you look at this particular graph, right? This curve does a beautiful job of reflecting what the data set does, right? It's got a perfect fit for the data set. But if you think about, boy, what should the line through this set of data look like? It probably should be more of a nice smooth curve, right? Rather than absolutely perfectly fitting to the data. And similarly, if we don't do enough fitting, we end up with a big error for any points that are not in our system. And I can't tell you why that error is going horizontally there or perpendicular here. You can congratulate me on using an image from somebody else. But anyway, we can also talk about post-processing your output layer. Remember I said that usually all of our neurons use the same activation function inside of them. Sometimes you might want to take the output from your output layer and run it through a post-processor before you actually produce your final output. For example, softmax is a activation function that takes whatever your output is and resets it so that it's the sum of all your output layer values is 1, right? So it's just sort of like, yeah, here you go. Convert output data into what we would call probability data, right? All the outputs sum to 1. You can also use argmax function, which says, let me find out which of these is the biggest, and I'm going to output 0 for everybody else and 1 and look really confident, right? So again, we're only using argmax on this, on the final output result. We are not, we're using a different activation function for all the other neurons. Remember, of course, that we sometimes might want to do classification. We've been doing regression with our continuous output features, right? But it's pretty easy to measure error when we're doing a regression problem. But, if your answer is for a fraudulent transaction, yes or no, right? Then we need to make sure that our output is yes or no. Lots of ways to do that, right? One of them, if you really just want to do the binary domain, is you can, figure out that take your output like a probability and use a sigmoid function where, you just say no is 0, yes is 1, and that's what you're trying to train to. And, or use some other function. You can also just use a, argmax layer at the end to pick the one with the highest output. And right, just to make sure you're familiar with all of these terms, we don't count the, when we talk about an input layer, these aren't actually neurons, right? These are your input values that you then multiply by that this neuron gets as input after being multiplied by a weight on this plus adding the bias, right? These guys aren't actually neurons, but this hidden layer are neurons. This layer is neurons. If we're talking about a multi-layer neural network, then we have multiple sort of, in this image, we would talk about, the vertical lines of neurons, right? So nothing from this layer, well, every neuron on this layer here is um, is only connected, only gets input from the left side, only gives output to the right side. There's no sort of looping back in here. And, or, I mean, you could imagine you could set these up with all sorts of different uh, geometries, but in practice, most people just have layers of neurons, maybe just one hidden layer, maybe multiple hidden layers. Um, so what have I got here? Multi-layer means that there are more than just a single layer of neurons doing the computations, and the input layer doesn't count because they're not really uh, um, neurons. We talked about what I mean by layers, or what people mean by layers, and the feed forward just means there aren't any loops in this geometry. It's always moving forward. Um, and again, people are very loosey-goosey with the term perceptron. Some people say multi-layer perceptron, um, even though this is using normal neurons and not perceptrons. Okay, so let's just talk about one particular application of neural networks, which is a very early, one of the earliest autonomous vehicles, ALVINN. Um, and ALVINN stood for Autonomous Land Vehicle in a Neural Network. Mid 90s, ALVINN was already working, but easy to understand. So I thought it would make a nice case study. You're getting an image as input, trying to control the vehicle as output. Um, Whenever we talk about, designing a neural net, the design is the hard part, right? It's just like, the wheel is really obvious once you see one. Um, and, I like to ask the question, would you ride around in a car at 65 miles an hour that's controlled by a neural net? Uh, People are doing it. Um, what about one that's controlled by a pigeon, right? We saw that pigeon before that could distinguish between Monet and Picasso. Uh, how much smarter are neural networks than pigeons? I don't know. Pigeons probably get bored. Um, anyway, in the 1990s, 480 by 512 pixel images was pretty common. And this system, the earliest versions of this system, just used that a single image from the camera, or a sequence of image, obviously, from the video camera. Later versions included range data, and so this is a scanning laser, the output from a scanning laser rangefinder, um, where dark areas mean closer and light areas mean further away. Way too much data in the 1980s and 90s, possibly too much data for computing today. And so the actual input images that they used for this system were 30 by 32 pixels, which is shockingly small, really. Um, and they took the laser range data and put it into an 8 by 32 pixel image. Um, they did some additional pre-processing on the images um, to take the 3 RGB input levels and turn it into a single grayscale level. I can't really give you a good reason for this activation. Dean Pomerleau, who invented this system, had some arguments for why these terms were useful. But I think, again, this is a case of, well, it worked, so we're going to use it. So we've got our input, right? And he decided he was going to use 9 hidden inputs. The more advanced system used 29 hidden units. And what should your output layer report? Well, similarly to what we were doing with our number detector, right, where we sort of had each output unit gave a sort of a confidence level as to what number we saw. Um, the ALVINN system did steering wheel angle, right? Am I turning my steering wheel sharp to the left, sharp to the right, straight ahead? And so there were 45 output units that each gave a continuous value from 0 to 1 of what, by continuous, I mean not discrete, right? The output was like the output on our numbers. It was a multi-layer feed forward neural network, right? So it was in layers, it was fully connected. Every neuron was fully connected to every node in the next layer and was connected to all the inputs from the previous layer. Training is really important, as you can imagine, in neural networks. And so the initial version of ALVINN could could build a reasonable set of weights after running, say, 30 to 40 epochs of these 1200 scenes for a single lane test, and could go, almost 4 miles an hour. But it took a long time to generate the synthetic road scenes. We could do that much faster now. It took a lot of training. We could do that much faster now. Couldn't really do it on more than a single lane road. Maybe we should say hooray that it was too difficult, because I think the solution that Pomerleau came up with was a much better and more realistic approach. Watch a human drive and use that as an example. So you get a screen, you get a screen capture of what the camera on the vehicle sees, and you look at what is the steering angle, and you say, great, this is what I'm going to do. Except that humans don't usually go off the road. And the robot actually needs to learn how it should recover if it makes an error, right? Because humans, if you think about humans driving, most of the time, if we're trying to stay on a road, we're not turning the steering wheel very much. So the robot is overlearning the drive straight technique. And so what Pomerleau did was he took his original image and made a set of 10 additional shifted images, and with corresponding training outputs with shifted steering angles. And so now he was teaching the robot to do a better job of staying on the road. Final ALVINN algorithm was called the training on the fly. We're not going to talk about how to bootstrap stuff, but once you're going, if you imagine you have 100 images in your training cache, you update the training data set every epoch by grabbing a single image with the camera, creating an additional 14 images like I talked about before with steering wheel angles based on your original, so shift 7 times to the left and 7 times to the right. Randomly throw out 15 old images from your training cache and replace them with these new 15 images you just generated. Tweak the weights, and it was about 50 epochs, and bing, bang, boom, you were training on the fly. And the steering direction that was chosen was, you can imagine that the outputs on the output layer of the neural network, you ended up with a sort of a bell curve, and so you figured out where the tip of that bell curve was. This is a picture of the vehicle that ALVINN ran on first, and the first version of ALVINN, it was an old Chevy van that was reconfigured to have a hydraulic transmission so that it could drive accurately at very low speeds. And this is people in the back of the van with the antique computers at the time. The newer version of ALVINN worked on an Army Humvee ambulance. It was an ambulance because, of course, computers were huge, and this is one of those CRT monitors that sticks out way far in the back. And so the ambulance gave lots of room in the back to drive. Here's your Spark Station, up to 64 megabytes of RAM. Wow, megabytes, right? This is what it was running on. Training on the fly requires about 2 minutes, during which a person drives about a quarter to a half a mile down the road, and can drive at 55 miles an hour on the highway. And it's driven for up to 90 miles without human intervention back in 1994. How do we evaluate network confidence? We can take a look at the output layers, and if they are giving a value between 0 and 1, we can see how big are those values. One of the things, this was Dean Pomerleau's PhD thesis, of course, so one of the things that he tried to do was some analysis of what's going on with the input weights and the output weights. So if you think about one of the hidden units, right? So take one hidden unit in the middle of that layer, and this dark represents a very low weight on the input to the hidden unit, multiplying by this pixel, right? And also a lower rate, but as we get in here, we've got a much higher weight to the input, and then the output weights from this neuron that go to the directional output units are shown in this line, right? So you can imagine your neuron sort of in between these guys. And Pomerleau tried to explain what these hidden units had learned. I'm not entirely persuaded that I can look at this picture and say, oh yeah, that's definitely non-road versus road, but it's kind of persuading, right? I'm a little bit confused as to why we've got some white in there, but and there are other explanations of what the weights actually mean, and it's certainly interesting to look at the weights. Again, it's not such explainable AI, so it's a little bit, a little bit what's the word I'm looking for, folks? A little bit not explainable, I guess, right? Which is often an issue. But in the big scheme of things, really relative, not so much processing, and it resulted in a system that could do autonomous driving pretty darn well. So I will stop there.